Hello everyone, welcome to the 8th and final video in the linear algebra lecture series. In this video we will use all the concepts that we discussed before. We will talk about an application of linear algebra, which is in systems of linear differential equations. So we have not covered many applications, but what we will cover now is very important for engineering because linear differential equations pop up everywhere. So a system of linear differential equations, we define that to be this thing. So it is in a way a linear system where every of our variables are now differentiable functions, and on the left hand side we have our b vector as a column which collects all the derivatives of these functions. So we can write a system in this way. So yeah, we again have a coefficient matrix A, we have a vector valued function which collects all of our functions, and then we have its derivative on the left hand side, where the derivative is just defined to be the element-wise derivative. Right, so we can rephrase this in terms of an initial value problem. As you should know from the lecture on differential equations and maybe the videos on differential equations, that differential equations only have unique solutions if the initial conditions are specified. So our problem is as follows. We want, given a system of linear differential equations and the initial condition, which is this x of 0 is x0, which is some n vector, we want to find x of t. So we want to find our vector valued function that satisfies this equation, given a and given our initial condition. So to get some intuition behind where the following definition, which is the definition of a matrix exponential, where this comes from, we will look at the case where n is 1. So a is a scalar. So we let a be just some scalar, and we have a scalar differential equation. So our x and x dot, they are just scalar functions. Now, you should know how to solve this. We just simply separate variables, and we see that we obtain this solution. So x of t is c e to the at, where c is some scalar that we are free to choose, and which depends on the initial condition. And this motivates us to define a matrix exponential. So we want to see if we can somehow generalize this result to the case where this a is not a scalar but a matrix. So yeah, we define a matrix exponential. So let A be a square matrix, then we define e to the power of a, so where a is the matrix, we define that to be this sum. So this is an infinite sum of matrices, and we say that a to the 0 is the identity matrix. So how would this look? So if you write this out, we get e to the a is first we have, so we have the first term is 0 factorial, which is 1, so we just ignore that. We have a to the 0, which is I to be by definition. Then we have a to the 1 over 1 factorial, so that is just a. Then we have a squared over 2. It looks a bit weird to put a matrix in a fraction, so we can just write a half squared. And then we get, we get 1 over 3 factorial, a cubed, and so on up until infinity. And what you can show is that this sum actually converges, and it converges uniformly, and we will need this property in a little bit. Yeah, so exactly, this is what I just showed you. This is basically in some sense a Taylor series of e to the x evaluated at a. So if we write out this Taylor series, if we substitute for every x we substitute a, we get what we had here. And now we have a very nice result, which will allow us to solve our initial value problem. So if we take the derivative of e to the at, and this t is just some scalar that we've chosen now, and we multiply a by the scalar from the right hand side, and we take the matrix exponential of that, and we then differentiate it. We want to calculate what this is. So first we write out what it is according to the definition. So we plug plug at into here. We set this derivative outside. Now, as I mentioned before, this sum converges uniformly, so we can take the derivative inside, and we just how do you say? We expand out these brackets, and we put the powers on a and on t. Then we take the derivative, so we multiply by n, so this n factorial reduces to n minus 1 factorial, and this t becomes t to the n minus 1. Then we do a change of variable. So yeah, okay, we do two steps in one here. First we take out an a, and then this becomes a to the n minus 1, and then we define L to be n minus 1, so then our sum runs from L equals 0 up to infinity, and we get a to the L, t to the L over L factorial, but that is just the same as e to the at, as we saw before. So what we have now shown is that the derivative of the matrix exponential of at is just a times e to the at. So this is a very, very, very nice result. And in this way, actually, the matrix exponential behaves exactly like the normal exponential, because if you would remember from calculus, if you have this expression, then all you have to do is take the a down, and there you have the derivative. And it translates exactly the same way to the matrix exponential. So this is a very, very nice result, and this will allow us to solve our initial value problem. So exactly, we will now solve the problem. And if we, in particular, then take this solution and we plug this in, we see that taking the derivative, we can take out this x0 term. We get e a to the at, but that is just the same as a times our xt, which we had before. This is our xt, and this is exactly what we wanted, so it works. Okay, this is all nice, but there's still a very, very, very big problem, which is computing this exponential, because we have to sum infinitely many terms, and it can be very, very difficult to compute this. And we will cover one case in particular where it is easy to compute the matrix exponential, which is when a is diagonalizable. So exactly, we'll compute the matrix exponential for diagonalizable matrices. Okay, suppose a is diagonalizable, then we have this matrix X and this matrix T, such that a can be decomposed in this way, and we will now show that this exponential is something. So let's just go through the proof, and then you will see where it comes from. So first we have this, as we saw before, we expand out this exponent that is normally here, and then we substitute what we know for what we know to be true for a. So we can just rewrite a in this way, because it is diagonalizable. Then in the theorem that we proved in the section about diagonalizability, we showed that raising a diagonalizable matrix to a power is the same as just raising the diagonal matrix to which it's similar to the same power. So we can just take this power in and just put it on D. Then we can interchange the scalar and this matrix, and then move the x inverse here and the x here outside of the sum, because they do not depend on n. But if you look at this is just the matrix exponential of dt, sorry. So we have now shown that if a is diagonalizable, then we can write its matrix exponential in this way. And now there is the following result, which is a bit tricky to show, but I leave it to you as an exercise, because I believe now after watching these videos you'll have some knowledge of linear algebra, and maybe also you've watched the calculus videos, and maybe you're itching to prove some things, so you can prove this result if you want. You can show that the exponential of a diagonal matrix is just a matrix with the elements of this matrix on its diagonal also raised, exponentiated. And you also have this t here. Yeah. Okay. Now that we know how to compute this matrix exponential, we will show it in an example. So we have this initial value problem. So this is our system of linear differential equations. These are our initial conditions. So we begin by writing it in matrix form. So we collect our equations here, and we get our coefficient matrix and our initial condition vector, which is 2, 2, 2. And we want to check if A is diagonalizable, because if it is, then it is quite easy to compute its matrix exponential, as we just saw. So to compute the matrix exponential, we will need to check if A is diagonalizable first, and then we can diagonalize it. So we first compute the eigenvalues of A by setting the determinant of A minus lambda I to 0. So this is A that we saw before. This is lambda I, so we subtract those two. Then we have the determinant. So we work this out. You can check all the calculations if you want, but you can also just believe me. Then it works out to this. And in the end, after some simplification, we get this polynomial. So minus lambda cubed plus lambda is equal to 0. And from this, we find the following eigenvalues. So lambda is 0, or lambda is 1 or minus 1. As these are distinct eigenvalues, and our matrix is a 3 by 3 matrix, so we have 3 distinct eigenvalues for a 3 by 3 matrix. You should recall that this implies that all of the eigenvectors are linearly independent, so our matrix is diagonalizable. Exactly, so the spectrum of A contains 3 distinct eigenvalues, so A is diagonalizable. Then, what we can do is we recall that our matrix D will have the eigenvalues of A on its diagonal, so 0, 1, and this minus 1, and that its exponential will have the diagonal entries of D exponentiated times times t. So here we get e to the 0t, which is 1, e to the 1t, which is e to the t, and e to the minus 1t, which is exactly what is this. Then, to find the non-singular x, so we showed before that this is true if A is diagonalizable. So now we want to find this x. And to do that, we compute the eigenvectors of A. So we need to find solutions, non-zero solutions actually, to this system for every lambda in the spectrum of A. So for lambda equals 0, we do it like this. We do some row operations, and we find this. So we have a free variable, which we expect for an eigenvector, and we find the corresponding eigenvector. You can check this if you want again. I will not go to the calculations in detail in this video, because you are free to pause the video and check them by yourself. Okay, moving on through a similar process. So also taking lambda as 1 and lambda as minus 1, we find these eigenvectors, and thus we obtain our matrix X like so, just by putting so important thing, this vector has corresponding eigenvalue lambda 1. This one has corresponding eigenvalue lambda 2 is equal to 1, and this one is eigenvalue lambda 3 is equal to minus 1. And it's important that the columns of X correspond like so. So the second column of X, the eigenvector you put there, corresponds to the second second non-zero entry of D, in the way that so that they correspond in this way. Does that make sense? Let me say it again. So the first column of X should correspond to the right eigenvalue, which is the first eigenvalue of D. So the eigenvalue corresponding to this eigenvector should go in the first spot, this one should go in the second one, this should go in the third, and so on. If you do not do this, then your decomposition will not work. The computation of this inverse is done by reducing xi, so this augmented matrix, to a reduced row echelon form. I have not covered this in the lectures, but you can just take it from me that it works. Okay, with that we have decomposed our matrix. We have x, t, and x inverse, and we also have e to the dt. So now the only thing we need to do is carry out our computation. So let's do that. Right, so we recall that our solution was this, the exponential of a times t and then our initial condition vector. So we saw that A was diagonalizable, so we decompose it in this way, multiply by x0, and now we just simply plug in what we found. So we found that this was x, this was e to the dt, this was x inverse, and this is x0. And now we have 20 more slides of matrix multiplication. Just kidding, you can check this product by yourself, the calculator or anything. No sane person would compute this by hand. And yeah, so this should be our result. So this is our vector valued function that satisfies our differential equation, system of differential equations, I should say. So this one. Okay, that is the end of this video and also the end of the videos overall. This is the last one. I hope you liked them. I wanted to remind you also that if there was some part of the videos where I made a mistake or something was unclear, you can always email me and I will reply as quickly as I can. I hope you enjoyed the videos, and I will see you at the lecture, hopefully. Bye bye.